Okay, good morning to you all. We have been late, sorry for that. So we will continue, and today we are discussing more on the design aspect and hydrokinetics. The terms seems not really familiar, but it's like both are related, hydro and kinetics. Kinetics is mostly we deal with the stability, and hydro we call it like a simple term, the seepage. So it's basically hydrokinetics is seepage and stability. And in tailings they are very much related. So you cannot separate them. That's the main concept of tailing compared to the hydro dam. Because the seepage is very important in the tailings. That's controlling the stability also. And where we left yesterday, I want to little bit touch on that. Like yesterday I left here, like we little bit discussed about CPT. So these are the two concepts we are saying, like regular CPT or a seismic CPT. So in regular CPT we have only one cone, and once you do that, then go to the bottom, then we switch to the seismic CPT where we send a geo cone to the bottom and then scan it and collect the yesterday I showed you, like we can collect the longitudinal and both longitudinal and shear velocity. Again, besides normal CPT and seismic CPT, we also do another very important is the pore pressure dissipation test. That's where I mentioned, like once we see this is the high dynamic pressure, we do that. So in the dissipation test, it's just an example you can see. That also tells us what's the material there. Whether it's a latent like sandy kind of behavior like a drained material or a undrained material. So you can see different curve, dissipation water test curve also can decide that. This is an example again, and we have three important parameters we are getting from the CPT. First parameter is the cone tip resistance, QT. The second parameter is the friction ratio, like along with the QT, we get also a slip friction. So the ratio of slip friction to QT is the friction ratio. Friction ratio is also important. And then the pore pressure. So you can see here, the basic distinction is whether it is drained or undrained. That is what we have to always find. Drained or undrained, we are telling it is sand or clay. So you can see in all these three parameters, you can identify whether it is a clay behavior or a sand behavior. It is only behavior. It's not necessarily this is like clay or this is like sand. It's like showing us that behavior. And again you can see you have the dynamic and also static. That U0 is the static one, what you are getting from the pore pressure dissipation test, and the dynamic one. I think somebody asked me like, what's the real difference between dynamic and static? So the good example is difference between a seismic event or a normal event. So if you have read like seen about what is the effect of groundwater during seismic event, what happens? You see the groundwater rises during seismic event. There will be a big rise in the groundwater and the pore pressure also increases during the seismic event. And that kind of seismic event is generated when we are driving a core. So that's how we get that, we call it a dynamic pore pressure. But for regular event, like we are mostly where it is seismically active region, definitely the dynamic pore pressure also helpful. But in most of the cases, we look into an area where it is not seismic active, but the normal, we call it static liquefaction. In those static liquefaction, our static pore pressure is important. What kind of parameter we get from CPT? You get also soil unit weight and overburden. You get the stratigraphy. You see that yesterday I showed you what are the like different layers you can identify. State, critical state, what the soil state and stress history. You get also effective friction angle and drain strength. From that, like I think you were asking, like why, how can we get drain strength? Yes, you can get that also from there. But again, these are all interpretations, and you have to be good understanding everything for the interpretation. The most important parameter which I focus from the CPT is the on-drain shear strength, because all other parameters I can still get from the lab test, but this on-drain shear strength is very difficult to get from the lab. Then you get also ground stiffness and soil modeling, like when we do numerical modeling, the Young's modulus is a very important parameter for the stress deformation analysis. Where you get that? Then the flow parameter also we get from CPT, because we do those pore pressure dissipation test. From there also we can derive permeability and other flow parameters. Then the liquefaction also we get our steady state strength or the residual strength which is needed for the liquefaction, and that also we get from this. Again, currently research is going on how AI can interpret all these parameters from the CPT data. This is the next kind of research is going on, how artificial intelligence can do that. Okay, now we come to, so from the CPT we collect all these parameters, and now we come to the fundamental our seepage and stability analysis. Mostly I am showing you the fundamentals because these are very important for the concept. So you can see that you can have a proper internal zoning. That what we normally assume, that there is a proper zoning. Very close to the face, we have a sand kind of material which is high permeability sand. Then in between we call it like a intermediate tailings, and then at the end where we see some water also, which I mentioned last time, that's the pond, supernatant pond there, and below it all the pines are there. If it is very proper, our tailings, this is again under upstream conditions. If it is very good zoning, then you see kind of a very well-defined cratic surface can be generated from here. So that's how we do this bed. So that's why you see that K1, K2, K3, that's the K1 is higher than K2 and higher than K3. But lot of time in reality or in practical field, we do not get that. Because initially it was very difficult because now with cyclone, we are able to differentiate fines and sand. Previously not there. It was very, we are thinking that the fines automatically, if we put along a slope, fines automatically go further and course will stay closer to the where we are putting them. But in reality it may not happen. So some cases we see that we have very low permeable along the face. Where it should be high permeable, we see that there are low permeable. So what it will do, it will block the seepage. If it blocks the seepage, you can see that you have higher phreatic surface. Then third case, also we have core, and mostly along the downstream phases we will see that our K1 and is also higher than K2 because there is a zone there, and the K1 is the mostly rock fill is high permeable material we use. So in that case, in downstream you will see this kind of seepage. But again, due to if you have like a core which is lower than K1, then it can also block the seepage and make the pore pressure high. So these are all concepts I am showing where you can see that the main goal is we have to make sure that the pore pressure is always low, means the high phreatic surface doesn't develop there. Again, you can, that's where we come up with those, remember in the mostly downstream and central line, we are showing you the use of the filter. So if you put the filter, then that also keep the pore pressure down. So that's another important, we do that in the downstream and central line. Again, in the upstream, also you can use a drain blanket at the bottom. You can use a drain blanket at the bottom to bring this pore pressure or the phreatic surface down. And in case of downstream, this chimney and then the blanket drain also you can see that the pore pressure on your downside. Main thing is we have to see what is happening on the downside. On the pond side, water pressure can stay higher. It doesn't matter. But what is happening in the downside? So that's why we are putting this kind of blanket like a filter, inclined chimney and a blanket drain to make the seepage, everything goes down and we do not see any phreatic surface developed within the dam. Same thing also we can see on the central line embankment. Same thing happens, the water surface intersect the filter and then everything goes up. So that keeps the dam safe. Again we see slime and sand in the upstream. You can see even it is sand, but you see the pore pressure or the phreatic surface is higher. If you go to a downstream or a central line, you can bring it down. So that is the useful for the central line and downstream versus the upstream. Upstream always we see higher phreatic surface for the higher pore pressure. But again, we do lot of control also, because there will be seepage. It's unavoidable because water is there, and these tailings material, they have also sand and clay, all these kind of things that can make the path for the seepage coming down. So we can do some control measure is we do cut-off trench, slurry wall, grout curtain. Also we put liner, and also we put some extraction well, mostly on the downstream side. We put all these measures on the downstream side to keep our surrounding environment safe. So those seepage, even if it will come out of the tailings, we can collect it and we can keep it. We do not want it to go further. So these are the control we do. Then come to the stability analysis. So when we do the stability analysis of any slope, because it is a slope, tailings dams is a slope, any stability analysis, one of the input is the phreatic surface. When we do the limit equilibrium method stability analysis, one of the input is the phreatic surface. And that phreatic surface can be also in pore pressure. So that can also be an input. So once we have that, then we do the stability analysis. Here a simple concept we are showing, like initially when we develop a starter dam, our mostly load, the pore pressure is the load of that dam. So that is the static pore water pressure. US is the static pore water pressure at that particular point. Now you are raising it. You add another layer of thickness H. So what it does to that pore pressure? It is adding excess pore pressure to that point. So your static pore water pressure, and then you are now adding another excess pore water pressure. And if a failure developed, like you have a critical failure surface which developed, then that will again generate some shearing pore pressure, another extra pore pressure. That's why you have this is coming, the pore pressure generated. This is a new additional pore pressure generated due to shearing, which call it UM. So at that particular point, the pore pressure is a combination of all these three forces: additional load and also failure. And that's why the total pore pressure is now static load plus excessive pore pressure plus shearing pore pressure. This is a very, very simple concept. And that's why when we are raising all these three things, we have to estimate. Why it's not moving? Satyam. Stop. Okay. Again, the conceptual stability analysis. Everything started, I am again going back to the hydro dam. If everything started from the hydro dam. In case of, that's why I am showing here the hydro dam. How we analyze hydro dam? We do a end of construction. We also do stage construction. We also do long-term steady seepage after everything is done in the long-term steady seepage, and also we do rapid drawdown in case of the hydro dam. In tailings, end of construction is also required, though the end of construction will continue with time, because when you are raising now, your end of construction is the first. Like when you go to the second stage, your end of construction is the first stage. When you are going to the third stage, your end of construction is the second stage. So it will just move. End of construction is not a one-time thing. But again, the long-term steady state seepage, that will come after the closure in case of the tailings. And then rapid drawdown is maybe in like a heavily wet area where you have large quantity of water in it. Rapid drawdown can be useful. Otherwise, in case of tailings, we don't see that effect of rapid drawdown, because most of these things are full with the tailings, and we have very small portion of the storm water or water present there, because most of the water is always recycled. Like when the tailings is settling, so the suspended solid settles and the water is again pumped out there, because water is recycled. That's the technology mostly everybody follows. But the end of construction also needed in case of a starter dam. That's also very important. In case of a starter dam, we need a end of construction condition. If the soil is mostly like clay, like undrained clay soil present, in the next session I will show you one example also, how that foundation soil again contribute to what kind of method we can choose for our tailings design. So in this type of loading, I can show you another, go to the next slide. You see, you have soft clay. Whether it is again in case of a other central line dam or upstream dam, also we have a slide tailings, because in the upstream dam your foundation is the tailings, and in the starter dam you have a soft clay. If you have a soft clay, that this is the condition. If you have a soft clay in your foundation, because most of the plain areas where we design either this, you have a plant and near the plant you are designing the tailings dam. In those areas it's possible you have some soft clay there. So there you have to consider this is the undrained conditions. And the tailings are always undrained. So in the undrained, this is the one like I mentioned before. My target is this SU, shear strength undrained. This parameter is a very, very critical parameter for the tailings. And whatever you do, which method you follow, you should have knowledge about the undrained shear strength, which we will again discuss more. Again, you can see how stage by stage we do. So, how the pore pressure is now increasing when you raise it. First phase, then it is excess pore pressure and the static pore pressure, U1 plus US1. When we go to the second stage, then it's all become U2, S2, because load is added and also extra load is adding to the next stage. So when you go to the stage 3, this is how with time, because these are all progressing with time. That's why in the tailings, it's all depend on the time. That's why in the initial I said hydro dam is a static dam, tailings dam is a dynamic dam. What is dynamic? Anything that changes with the time is the dynamic. So here you can see how when we are adding, how the things are changing. And in the long term, once everything is done, like this is after closure. After closure, again we should have a phreatic surface, and during construction time, definitely we use little bit steeper slope, but at the closure, it has to be 3-to-1 slope. There are so many other factors also, not only stability, because for stability, you can be higher than 3-to-1 slope, but mainly for the erosion and also for other activities, we prefer anything lower than the 3-to-1, like higher than 3-to-1 slope. Some cases we can go also 4-to-1 slope, this at the end. So this is if it is a completely drained condition, which we think in the long term it will be a drained condition, like if it's phreatic surface, there is a clear cut developed phreatic surface, then it can be a drained condition. So in case of drained condition, you don't need your C0 and you have your P depending on the what kind of material. But most of the time, we see that below the phreatic surface, we have that undrained condition. We are seeing that even in, I have investigated some tailings dams which are closed for 20 years and 30 years. But when we go and investigate that, we see that they are still under undrained conditions. So under undrained conditions, you will have this total stress. This is the total stress. Under drained condition, we call it effective stress condition. So under total stress condition, you have also a friction angle total and also a C cohesion total, which is this, that C total is same as the SU, undrained shear strength. So this is, I think yesterday somebody asked me like, why you need numerical model? We have an empirical model, we can do that. Like limit equilibrium method, we can solve it. But the limit equilibrium method, the limit is a limit equilibrium method, but there is a limit to it. That's why currently like last I attended the tailings dam conference. So at the end of the conference, there was a consensus that limit equilibrium method is not applicable for the tailings. But I will not make that statement. Yes, under design, like in the initial design stage, still we can use limit equilibrium method and come up with a simple solutions. So that's for a starter dam design and things, we can do that. But under stage condition, as we go on the operations, you need a numerical model. One of the example I will show you. Say this is the like you see, this is the current existing dam, and what the empty space you are seeing there, we are building it. In time, we are going up, up, up. So this is the initial pore pressure or water table. this is like again, I mentioned you, in the tailings dams, you never will see like a full-fledged phreatic surface. That may not develop, or it may take more time to develop. During the construction stage, it may not be there, but you can have an assumptions. And then, in the limit equilibrium model, you have to have a phreatic surface. It will not give you any phreatic surface. But when I am designing this, how do I know what will be the phreatic surface at the end? But I need that during my design. So I will develop a numerical model. I will just briefly show you that. Oh, you can see here how this is generated. You see, this is generated using a numerical model. So now at that stage, that's my end stage, this is our pore pressure. And we can use that to develop a limit equilibrium model. In the limit equilibrium model, this is using GeoStudio. The CW model, like that seepage model you saw earlier, that was using the CW. Then we combine CW and slope W. So the pore pressure generated by CW is now used in the slope W to calculate the factor of safety. So that's why in tailings a numerical model is a must, and in the currently state of the art is most of the even the client, they are coming to us develop the 3D model. That's what we are doing. But mostly is the seepage model. And once we develop the seepage model, and then it's not the final, like this is initial stage, we come up with that. But with time, like every 4 to 5 years, we will go and refine our model, because in 5 years we will collect more data. You see those points, P3, S4A, U4A, these are some existing piezometer there. But as you go on, we go on installing more and more piezometer in the higher level. And that piezometer will give us the pore pressure. And we also compare what is our model and what is the exact what we are getting. If there is any discrepancy, we again come back to our numerical model, refine it to match that. A lot of things I will show you in this day 4 and day 5. I will show you some more details. Static liquefaction. I think that's a big concept right now, because lot of these tailings dams, after failure, most of the people are saying it's due to static liquefaction, like Mount Pauling is again the static liquefaction, and the Brazilian failure also related to static liquefaction. You saw that, like how that whole thing liquefied and progressed. So the static liquefaction, you can see that you have a pore pressure in the bottom. There is a small pocket of pore pressure is there, and it's a rising, that pore pressure will rise with the load. So what are the conditions? It should be a loose soil. So mostly fine soils. If you remember yesterday I was showing you, those are the critical soils, CC and CCT is they are contracting, their value is low. So those kind of soil, they are loose soils. and also rapid loading. That's the very important. If you allow progressive loading, like you load it, but then allow some time to settle. But if you don't allow any time and go on loading, then this pore pressure can rapidly go. One example I can tell you, I did one modeling for a failure dam, how that failed. It was a old tailing pond, like 20 years old, 20 years it was inactive. Then the company, they decided that they need some space for the rock down, west rock down. So somebody told them, okay, there's a big space is there, it's a tailing dam, but big space is there, upper, if you go down on top of it, it looks very good, you walk on it looks very good, so you can dump there. They did also some stability model, limit equilibrium based stability model, and they designed it for 100 feet more dump on top of the tailings. So initially they put 50 feet, but all over the tailings, but when they go and put next 50 feet, it failed. So when I was analyzing the data, mostly coming from the CPT, we saw that we took some repeating test of the CPT. With time, the data we got 15 days after the failure, but I saw that the pore pressure is declining, like after the failure. So definitely at the time of failure, pore pressure was very high. So I back calculated that curve to see at the time of failure what is the pore pressure. So the pore pressure can increase very rapidly and also very high. And that 50 feet load, if they put within a month, if that 50 feet of load put in 2 years or 3 years of time, things could be completely different. That's why the rapid loading is the major concern. Then the on-range, that's again another conditions. We have to see that it's not on-range. And slope instability, like once it fails, it will start with a small failure. Like the Brazil dam failed, people said that it failed mainly due to that drilling they did. If they would not have done the drilling, that was one group came up with that cause of the failure of the drilling. That's also correct. Like once it started failure, it will progress. It can fail very small one, but gradually it will progress and make a big failure. Again, some of the concept, you see that critical state. So you see, normally we say we have three type of behavior, like a dense sand, it's like a sand, dilative, or a loose contractive stress sand, and the third one is the static liquefaction. Because its strength has now gone, still the loose contractive stress, it has some strength, but once it liquefies, there is no strength. It's kind of the same, it's a soil, but it behaves like a liquid. So that's why we call it a liquefaction process. So you can see that the difference with the dilative state and contractive states. The dilative states, strain hardening, while the contractive and other states is the strain softening. What is the strain softening and strain hardening? With the strain hardening is, with strain, strength is increasing. Strain softening is, with the strain, it is decreasing. So the on-range behavior comes from this. So this is a very simple concept, but This is how we define the liquefaction. Again, I saw also this slide, but that time I didn't go into more details. But normally, what are the failures and what is the current remedy? This is a kind of a summary. So, the failure modes are like can be overtopping, slope instability like this slope failure. There can be internal erosion. Most of the hydro dams we see the piping failure, internal erosion. There can be external erosion. If you go to the tailing site, any tailing site you visit, you will find some gullies, erosional gullies. So those are like external erosion. Again, earthquake, definitely failure can occur due to earthquake. And the decant system we use for the surface water, removal of surface water. If there is a failure of decant system, surface water cannot go and you get more and more surface water there can be. And some of the remedy, we use also some gabions or boro material or the material from the 9 feet materials to stop the overtopping, like increase your height, or we also design some emergency spillways and also the collection, like extra storm water is there, we through spillway it was diverted and there is extra storm water basin developed to store it, because if you don't have that basin then it will go unfolded. Slope stability, we also use some soil reinforcement. Again, drainage. If you have a good drainage, that helps a lot. That's why those downstream and central line, we have those filter and drainage, good draining system. Don't allow. The main aim is do not allow any pore pressure within the dam, not the tailings, but within the dam, like the upper part, like the side part, near the slope. There, any kind of pore pressure is not good for the structure. Internal erosion, like mostly downstream embankments are good for internal erosions. And for external erosion, if you really do vegetation and put some berms or put some riprap or rock fill, they helps. And earthquake, mainly if there is any crack, they will first fail during the earthquake. That is the first thing, you can see that. Then in the decant system, like if you are failure of a decant system, if you have a good spillway design, then that will help. This part will be covered in the next lecture, so I am skipping it. Some advances, technological advances. So in the recent year, I want to bring that. Increased improved technology like the cone penetration test. These are new. Before 2000, very few sites we have, but in US and Australia and Canada, currently every site we do CPT every 4 years. It's not that initially we do CPT, we do CPT, repeated CPT for every 4 years as we raise it. Then we have also water management. Initially people are not that much familiar with surface water, how to calculate it, but right now, I don't know what's the status in India, but in US, other places, this hydrology is very important, even much more than the structure in the civil engineering. Hydrology is main purpose. So that helps in the water management. What we normally do there in the new facility, which will be covered in our next slides in the details, but we put a storm water bypass. We do not allow any storm water into the tailings. They all diverted outside. Then also we have to look into this acid drainage, because all these tailings contain some, like most of the copper tailings and things, they have acid generated even with the precipitation. What is coming out is the all acid drainage. And we have to put great emphasis on the closure. That is how the GISTM is now focusing. Each tailing dams closure should be designed in the beginning. Though we will do that at the end, but in the beginning we should have a clear concept how we will close it. Again, the site investigation, like initially it was people, any design report I have reviewed before 1980, even before 2000, they were always using the drained parameters for the design. But when it fell, like I compared, like I studied a lot of tailings failures. So I compared what they did in the design and when it fell, what is coming out. So when it fell, I found everybody is focusing on the ongoing strength. But when the design, they use the drain strength. Because one of the things, like I have discussed with a lot of people, they say that, how can I determine the on-drain strength during design? I don't know anything. My answer is, how do you get the drain design also? You don't have anything, but you get some drain strength. One aspect of that is drain, the variation of drain strength is very, very little variation. It doesn't vary that much. So you can use conservatively for the drain parameter. But on drain strength, they vary a lot. Some improved design. So that's how we are doing now in the new facility. We put a liner. That's the most now. There will be a liner, so that liner protects any flow going to the groundwater. So that we are showing to our people, like the Greenpeace people or the environmental people, all the agencies, groundwater will not be affected at all. So the liner is there, and also we put some drainage layer. You can see that we put also some drainage layer. And in the liner, I think yesterday they were showing is, our system is a double liner, because we know that there will be some seepage. So between the liner, we put some material also. In the first liner, there will be some leakage. So it can be collected and go there. So we put like a double liner system. Those are the improved concepts. Again, the dewatering, the next phase which is coming, because what we discussed mostly is like a slurry form. But right now, a lot of research is going on, and I have some people there in the backside, they are saying we are preparing the dry stack. So you have, from the tailings slurry, you can have a thickened tailings, like you dewater it, you develop a paste, and further dewatering, you can develop a wet cake or a dry cake. That most of you will call it the dry stack. And basic things you can see, it's a least effective water conservation if it's with the slurry. And when you go to the dry stack, definitely you will conserve water. Especially in the state where I belong, we don't have much water there, it's a dry. The average rainfall is there 7 inches. So that's why there are a lot of technology developed, because they were forced to develop. How you can recycle, how you can save water. So definitely if you go through this dry stack, you can save water. and definitely the tailings would be more stable compared to that because your water is now less, and even lightning failure, what type of thing you saw in Brazil, and it can go to the river and can go further, this will be prevented in the dry stack. It will fail, like we have seen also some dry stack failure, but it will not be devastating, it will not go that far. So this is for the next generation, and the dry stack technology is coming. I think that's all for this today's lecture. And if you have any questions, okay.
Sir, good morning, sir. Sir, if a tailing material is prone to static liquefaction, what are the preventive measures we can take?
Like
you have shown that static liquefaction or that other part of liquefaction, dilation or contraction. So if a tailing material, if we find that the material is prone to static liquefaction, then what may be the precautionary measures we can take?
The precautionary measure is, like again, we are monitoring the pore pressure because the static, we know that it is prone to static liquefaction. But in the static liquefaction, there is a residual strain. So we have to make sure that it stays above the residual strain, because if it goes below the residual strain, it will fail. But that, whether, like how it will stay above the residual strength depend on the pore pressure. Because as pore pressure is increasing, strength is decreasing. So we monitor the pore pressure, and I mentioned, we have all these piezometers. Every piezometer has a threshold value, and that threshold value is normally 5 feet or 10 feet below the failure pore pressure. So if we see in our piezometer we are closing, like becoming nearer to threshold value, then we take some steps there. We identify those areas. The first step is to stop further loading, because it will go on increasing while you are loading. But the first thing is stop loading, stop operations. That is the first thing. Second thing is the dewater it. And I am not saying much on the dewater, but I will give you one example. There was a tailings dam. It was 30 years old, means for 30 years inactive. The client decided, like, we have extra material, can we use that? So that space is there. It was their old tailings facility. When I go there, the condition I saw, I came back, I told them, like, I don't need to do any seepage analysis or stability analysis. Based on my own experience, I can tell you, no. So then they found the issue, because the issue is the seepage. There is a lot of pore water pressure there. So they told me, like, can you dewater it? Because the cause is the dewatering. Again, also we have another solutions. We normally do, like, put some boron in front of it to stabilize this one. You can put some boron. But again, like we saw that failure, if it fails, that boron will not also help. So basically, I told them, like, the dewatering is not easy. It will be expensive. Like, again, we can do some pilot testing and do something. So I discourage them for the dewatering. So they again go back to another consultant. And they have used dewatering technology in some other sites. So they thought that, okay, we have used that and this can be used here also. So they go on and spend some money and collected some data there. And after spending close to 300,000, their answer was the same what I get. So the client again came back to me, you are right. I told, yeah, if you get some, we now get more data. It's not like wrong experiment. We get more data. Now we know more things there, so we can detect it. So the dewatering is not easy in the tailings, but it can be done. In some sites we have done that, like we do in the clay. Most of the clay materials, we also do some dewatering, weak drains. You have heard of that, weak drains?
Yes.
Weak drains we put. So similar technology can be adopted to tailings. But the problem is it's so vast. And if you put 5 feet spacing weak drains, then you can see the cost of doing that. And again, there is no guarantee that it will be fully successful. But we are doing some experiments, on site it is successful, but in general, we have to still look into that particular site and what is going on. But the thing is, if you identify the conditions, you take preventive measures, put some bombs and do something, and main thing is monitor it. That is what needed.
Sir, another thing, the tailing materials are majorly very fine materials.
Mm-hmm.
Are they prone to dynamic liquefaction?
During the earthquake, yes. Earthquake, that's also happens.
Yes, but in that case, the earthquake magnitude may be very big or high value, because these are very fine materials. I did some analysis for earthquake liquefaction or the dynamic liquefaction, and I found that these materials are more or less prone to, are not prone to liquefaction under say 0.16 G or 0.24 G. For liquefaction, dynamic liquefaction, you may go up to 0.36 G, then these are liquefiable.
I will give you, like we have a slide also for the earthquake on these things. I will show you some examples there. It all depends on the how much moisture content there, how much saturated is that tailings. If it is like fully saturated, then you are good. But the problem comes when they are partially saturated,
Yes,
like
yes.
80%. I will show that how the partially saturated is causing more damage to the tailings.
Sir, you mentioned in one of your previous slide that the surface water, we cannot allow the surface water to accumulate there. So what way we can divert the surface
Yeah,
water?
in our next session, we have a discussion on the surface water.
Okay.
We'll discuss
And this
that.
surface water is due to rain only, sir, or some other factors are also?
Mostly rain.
Rain
Mostly
only.
rain,
So,
yeah.
okay, you will show that way.
Yeah,
We
next-
can divert it.
Session will deal with that.
Yeah. And sir, you mentioned in stability of the slope that soil reinforcement also can be done in the tailings.
Mhm.
Because I have not heard about this, for whether soil reinforcement can be used in the tailings.
Mhm.
Like in infrastructure, like in bridges and all those flyovers, we have used the soil reinforcement.
Mhm.
But here also can be used the soil reinforcement.
Again, I will tell you, like when we do the closure, we also, the main soil reinforcement is some dewatering, like we can do some dewatering. And again, if we can identify a zone, like it's a prone to the erosion, so we can take some measures there also and do some kind of stabilize that slope using the same principle we are using the stabilizing other slopes.
So soil reinforcement can be used
Yeah,
here.
you can do
We
that.
can use that.
Yes, yes.
Okay.
But the thing is, these are huge. So we do it only on the specific locations. We do not do that for whole
Yeah.
dam. That is not viable.
So the critical areas where you see
Exactly.
that the slope failures will occur or there are
You have to identify that.
Right, and then we can do
Then we can do specific measurements we do.
for that particular area.
And mostly the reinforcement is the putting berms. That's the normal
Putting berms only.
Berms.
Oh, it is called soil reinforcement by through
by
berms.
putting berms.
Because in some bridges we put the reinforcement itself in the soil and then layer by layer we compact it.
The soil nailing.
Soil nailing.
Soil nailing. Now, in case of tailings, it is difficult to do that because it's already developed slopes. So the reinforcement are different. Like you have to flatten the slope, you have to dewater the slope, you have to put some berms. These kind of measures
Measurements.
you have to take.
No, sir, good morning, sir. So my question is about the rapid loading. So in the case of the tailings, you are saying that for the rapid loading, it will tends to liquefaction. So how we can decide that time period
Yeah.
which is sudden or which is?
Yeah, like I will show one example in coming classes where I will mention like what we recommend and how we recommend them that value. I show you that like how due to loading pore pressure is rising and what is a safe value because it will go on rising. But we want that it should not rise rapidly. Because if it rises rapidly, then you cannot control it. But you allow it to slowly rise and also stay stable for some period, that's how we manage it.
And also like how we calculate that time period actually. Like for the construction we are making in 1 month.
It's not like every month we do not say that, but I give them some recommendation about the annual rates, how much they can raise annually.
And
So that kind of recommendation we provide them.
thank you.